tells you microcontroller is something like a small controller. Okay, they are like single chip computers because microcomputers are available in chip form. So it is available in DIP packages. So they are like computers that often embedded into other systems to function as some kind of processing or either controlling unit. So now it has got a CPU. So it has got a CPU, which is otherwise called as the microprocessor unit. So in addition to it, you have a kind of fixed memory, like a fixed amount of RAM in that sense, ROM, and your IO parts, your input output ports, and the timer on a single chip. So all these are available on a single chip. So the fixed amount of on-chip RAM, ROM, timer, and IO parts in a microcontroller makes which is occupying less space. Okay, so this is an internal block diagram of typically just a layout of how generically a microcontroller will have in its internal look. So it's an internal block diagram. So it will have your microprocessor or the CPU for that matter. Then you have some amount of RAM and ROM, which is again on chip. So then you have the related IO ports to interface with other devices. Then you have inbuilt RAMs, analog to digital converters. You have serial input and output, and other devices like your counters. And all other devices are being connected via an system bus. Yes. So the common communication line is the system bus. So this microcontroller is a small computer which is going to perform specific task. So, so relatively, we have an example. We have an ample number of examples which are related where microcontrollers are employed, but very specifically, so very specifically, we have this microcontroller to work being employed in washing machines, your hand phones, your PD environments. All will have microcontroller for that matter. So these are the general purpose applications in the sense that the user are programmable facility also. So this is the specific task where microcontrollers drastically employed. So upon this, we just get into understand the difference between the microprocessor and the microcontroller. So if you just look into the internal block diagram itself, your microprocessors have all as separate units. You have a processing unit. So where we have seen it as an arithmetic and logic unit in your basic fundamental processor. So apart from your arithmetic and logic unit, so which comprise the CPU, then you have external ROM, you have external read bar write memory, then you have some different an individual module for serial interface, individual module for IO ports and timer. So all the elements are connected together by a wired concept. So then microprocessor do not have anything on chip. It is not all these facilities. You have to connect it if you want to use for specific purposes. So it do not have microprocessor do not have a read-only ROM, a RAM, or your serial interface modules or IO port modules or counter or timer modules. All you have to connect it. Okay. So that is the case with respect to microprocessor. When you contrast with your microcontroller has microprocessor in it, your timer, your IO port, your memory, everything is available on single chip. So everything is the inbuilt facilities. So here it's just a processor. Memory and outputs have to be connected. And then IO components all are connected within a single chip. So since if you understood that memory and IO has to be connected externally, your circuit becomes larger. So, but then in the case of microcontroller, you have the memory and the IOs internally, and everything is going in the name of nano and micro fabrication. So the ultimate um, size of the microcontroller is reduced. Okay, it cannot be used in compact systems because everything has to be connected externally, large enough when compared to that of your microcontroller. So when you look into the entire cost analysis, the cost of the entire system increases. So when you go for a bulk manufacturing of microcontrollers, your cost is very low. So wherein, but this case, you have to select your own memory system, you have timer circuit, your own IO ports, all that you have to chosen based on the application, and you have to connect processor. So the entire system cost will increase. But then this is all inbuilt. So what happens is that when you go for bulk manufacturing of your microcontroller chip, your cost is drastically reduced. So, and if you look into the power saving capabilities, your microprocessor do not have saving features, but then your most of your microcontrollers have power saving modes like your idle mode and power saving mode. So they have separate modes of operation wherein your power consumption is drastically reduced in those modes. So in that way, your power consumption is further reduced in case of microcontroller compared to that of your microprocessor. And if you understand, if you look into the internal organization, so microprocessor will have less number of registers and hence the operations are just memory based. Registers, and hence the programs are easier to write. Yes. And if you look into the architecture, I suppose we have discussed about the von Neumann architecture. So this is the basic architecture. So, and you have to understand that in that architecture, the program and the data is being stored in the same memory module. So whereas in your microcontroller, it works on hardware architecture, separate memory, and your data has got separate memory. So that is the advantages of switching over from von Neumann architecture to Harvard architecture. So that is the difference. Basically, major difference is that about the components that it has. So microcontroller has all inbuilt things. So it has inbuilt microprocessor, ROM, RAM, timer circuit, IO ports, interfacing, and serial communication. All there, everything is under one utility. So, so when you see the functional block, the memory and the other peripherals has to be connected externally in case of a microprocessor chip, and it is not in the case of microcontrollers. So microcontrollers have all these facilities on a single chip. Okay, so that is the advantages of. With that, we'll understand a small. So we have examples of microcontrollers. We have like Intel MCS microcontroller 8051. Then you have Atmel 89. You have Motorola microcontroller, PIC microcontroller. All are available. But in the syllabus, we are trying to discuss about 8051 microcontroller. Yes. So this 8051 controller is being designed by the Intel Corporation. So in the year 1981. So again, if you look into this, the features or basic details about this Intel 80 processor. So it is basically an 8-bit microcontroller. So this family, if you see this family of So Intel was the corporation to design this 8051 microcontroller. So it is an 8-bit microcontroller family and has got number of rangings right from your 8031 to 8751. And they are available in NMOS type. If you have understood about in your digital logics, what is NMOS, what is CMOS construction. So it is available in both construction modules and variety of packages. So we generally in laboratory we use 40 pin DIP package, that is your dual inline package. It is available as a chip, so that will sit in on in the circuit board to perform its operation. So this microcontroller has got 40 pins and 4 KB ROM storage, yes, and 128 bytes of RAM storage, yes, and it has got 2 timer circuits, 1 serial port. It has got 2 16-bit timers, 1 serial port, and 4 parallel 8-bit ports. Okay, so on a single chip, that you have to understand. All these are on a single chip. One in original member of 8051 family, and we refer it to as MCS51. Yes. Okay. And now, if you see this 4 parallel 8-bit ports, so it is programmable as well as addressable as per the requirement. Okay. So this microcontroller is going to operate. So we have understood about clock cycles. Yes. So that clock cycle is being, if you see, it has been, we are able to generate the clock cycle with help of this on-chip crystal oscillator. Okay, there are dedicated. This oscillator is going to generate clock cycles. So now here, this integrated microcontroller have crystal frequency of 12 megahertz. So the clock frequency is 12 megahertz with respect to your 8051. Yes, so this is the basic idea of Intel 8051 microcontroller. So let's get in detail about the features. So first important thing is that it is an 8-bit CPU. So it's an 8-bit microcontroller, as I told. So it is 8-bit CPU, and it has got 16-bit program counter. So what a program counter is? Program counter is nothing but it will store the address of the next instruction that is to be performed. So the address is going to be 16 bits long. So it is 16-bit program counter. Then you have something called as program status word. So first 16-bit program counter, it is going to give the 16-bit register giving the address of the next instruction to be executed in the program. Yes. So after that you have the program status word. So that we'll get into detail what is this program status word, because you have to understand before that little more about the basic process. Then we'll get into what is this program status word. So it is going to deal with the flags associated with it. So what are the status flags upon the operation? So all that will come under that program status word. So next you have something called as stack pointer. So stack pointer here is 8-bit. So this 8-bit, it is basically 8-bit register for that matter. So this stack pointer is going to keep the track of memory space where the important register informations are stored. Okay. So now say for instance, you have some interrupts coming up when executing a program, or else if you have some subroutine. So somewhere your address of the result previous address has to be stored. Result has to be stored somewhere. So you put those all information in the stack, and the point upon execution of the subroutine, it will come back from that point. So it is a pointer which keeps a track of the memory space where the important register being stored when the program flows get in execution of the subroutine. Okay. So it is the stack portion is maybe placed anywhere in your on-chip RAM. Okay. So but we'll understand about even the memory organization in the later part of the class, or later part of this lecture. Then we have apart from your stack pointer, you have internal RAM, which is of 128 bits, 128 bytes of internal RAM, which is an on-chip data memory. Okay. Then you have special function registers of 128 bytes. So we'll understand what is this special function register. Mm, uh, because we have number of special function registers which are associated with 8051. So these the address of the special function registers are again has specific location in the memory space. So we have many function, typically many special function registers like your accumulator, your data pointer, your power control, we have program status word, all registers associated. We have around 20 special function registers, which is of 128 bytes. Then apart from it, you have 32 IO pins. Okay, so we have 32 IO pins as 4 8-bit ports. So right from port 0, port 1, port 2, port 3. So these ports are for input and output purposes. So you have 32 pins. So 32 pins. So each port has 8 pins. So you have 32 IO pins arranged as 4 8-bit ports. So now you have so that is your T0 and T1. So that is a 216-bit timer or counter. It can act as a timer or a counter. And then you have two external and internal vector interrupts. So you have pins dedicatedly for interrupts also. It can be an external, two are external and 3 internal vector interrupts. And 1 full duplex serial input output. 1 full duplex. So you have to understand what is full duplex. So both way of data passing. So full duplex means the data can go both ways at the same time. So you have 1 full duplex serial input and output port. So this is the basic features when you look into the part of 8051 microcontroller. It has got 8-bit CPU. So the data bytes, so the data length is 8-bit, but you have 16-bit program counter means your address is 16-bit, and you have 8-bit process 8-bit process stated word or program status word. So this program status word is going to keep the status of your arithmetic and your logic operation in different bits. Okay, so you have the associated flags. So say for instance, whether if you have a carry, whether you have a 0 value, whether it is signed or unsigned value, all that is being that program status word or processor status word. So it is it is going to keep the current status of the arithmetic and the logic operation. So that you have a dedicated 8-bit process status word you have. Then you have 8-bit stack pointer. So stack pointer comes into picture when you are executing an interrupt or a subroutine. So after execution of the subroutine, it has to come to the main program. So that main program address where it has left last, right? That address is held in the stack. Okay, that is held in the stack pointer. So upon execution of the subroutine, what happens? Your stack pointer address is taken up and it starts executing in the main program. So that is the purpose of your stack pointer. So it is 8-bit long. Then you have internal RAM, 128 bits on-chip RAM. Then you have special function registers, which is of 128 bytes. Then you have 4 ports dedicated for input-output operations. So each port is 8-bit long. So you have 32 IO pins arranged. Then apart from it, you have 2 16-bit timer bar counter. So it can act as a timer or counter. So 2 16-bit timer or counter we have. Then you have 2 external interrupt pins and 3 internal vector interrupts facility over here. And you have 1 full duplex serial input output. So full duplex in a sense, you can pass data in the either ways, to and from. So both ways at the same time. Okay. So example of your full duplex is your telephonic conversation. Okay. full duplex is telephonic conversation. So the person from the other end also speak at a time. At the same time, the receiver also can speak at the same time. Okay, there is two-way communication at the same time. So, but when you go for half duplex example is your walkie-talkie. Only one person can communicate at a time. Either from a person A can communicate or person B can communicate. Yes, in a walkie-talkie application. So that is the prime difference between full duplex and half duplex. So in full duplex serial input communication, both ways. So your means that your data can go both ways at the same time. So these are the basic features of your 8051 microcontroller. So looking into the functional block diagram. So this is typically a functional block diagram of an 8051 microcontroller. As you see, you can have the central processing unit. So it is this functional this is the main important block. So this is the central processing unit. It is considered to be the brain of the microcontroller. Controllers. Okay, so this is the CPU. So reading user programs. So this does the process of reading user programs and executing the task accordingly. So the primary elements in it will be your accumulator, your register, your stack pointer, program counter, your program status word, and data pointer. All this will be available in the central processing unit. Then you have the interrupt control. So you have the features for external interrupt as well as from the internal interrupt. So this is the on the interrupts priority, your CPU will process the data accordingly. So now it is powered up. As I told, the clock frequency is generated with the oscillator, crystal oscillator. As you see, you have crystal oscillator you have. So it is going to generate clock signals. So based on those clock signal only, your entire 8051 microcontroller is going to function. Yes. So that is to do with your crystal oscillator. So this crystal oscillator will, as we have mentioned, it is going to generate clock pulses by which all the internal operations are being synchronized. So you have seen about in your microprocessor itself, we have seen the timing diagram. So for it is based upon the clock cycle only your instructions are being executed. So you have something like crystal 1 and 2. Just they are provided for connecting a resonant network to form an oscillator over here. So a crystal quartz crystal is being used for the purpose of oscillator. And now this is going to generate, this crystal frequency is going to be the basic internal clock frequency of the entire microcontroller unit. So all the internal operations are being synchronized with respect to this frequency. So next is your program memory. When you see program memory, you have got as you have already seen, we have 64K data memory space for address and 64K for data memory address space, and 128 on-chip data memory. Is it 4? No, it's 64. So it is 64K program memory. Yes. So that is the program memory and the memory associated. So you have on-chip program memory, you have on-chip data memory. So you have off-chip program memory, off-chip data memory. So there are even off-chip program memory also is possible. Okay. So all these are externally you can connect it. When you see you have 128 RAM locations. So this is 128 RAM locations. So on chip RAM, it's going to address single byte. So you have 128 RAM location. So you have to understand it is single byte wide. Okay, each of them are going to be. So apart from this, you have something like your 64 kilobyte of program memory space. It is 64. So it is going to consist of an internal and external memory portion. So when you look into when we are trying to understand the memory organization, then we'll discuss this in detail. How the organization is internal and the memory portions are being allocated. So apart from that, you have we have seen we have got two 16-bit timer bar counter. So this is T0 and T1, which is going to act as an timer or the counter operation. Then you have bus control signals. So that is 16-bit bus control signals. And you have, as we have already told, 4 input and output ports. Port 0. So we have got 4 8-bit ports. So port 0, port 1, port 2, port 3, which are for IO instruction. Address data for address communication. So you have dedicated serial interface. So you have respective pins like your transmit and receive data signals. So all the elements are being connected through a system bus. So system bus and the bus control signals. So bus control signals also you have. Then other devices like your program memory, ports, data memory, serial interface, interrupts, controls, your timer, your CPU, all are interfaced through this system bus. Yes. So the system has consists of data bus, address bus, and control bus, and all the devices are 51 microcontroller. Let's understand the pin diagram. So this is the 40 pin DIP package of an 8051. So you have first 8. So first 8 pins are for ports, IO ports. Then you have VCC over here. Then you have port 3, which is of dual purpose. Then you have clock frequency generator. So your crystal. So you will understand this. If you see the 16-bit address is being taken up by port 0 and port 2. So you can see your first from your pin number 32 to 39, it is port 0. So port 0, first 0th pin, first pin, second pin, third pin, 7 up to 7 pins. So these have dual purpose. It can access or data lines also, but wherein your port 2, that is from pin number 21 to 28, it is going to act only as address bus. Okay, so that is the difference. So by having this ALE operation, ALE is whether you are operating it to be an address or data bus, it can act as either address bus or data bus, but your functionalities over here. Yes, and your port 2 pin has got specific to only your input and outputs, and we'll see this all in the we'll explain each the functionalities of each pin. So first is pin 1 to 8. So pin 1 to 8 is going to be the pin. If you see port 1, your pin 1 to 8, pin 1 to 8 are dedicated for port 1. So port 1 is used either as input or output only. So it does not have any dual functions like the rest of the ports. So to make the port 1 as input port, you have to write value 1 to all 8 bits. So when you pass 1 through all the bits, now this port is going to act as an input port. So when you make the port 1 as an output port, then you have to write 0. Yes. So when it is if all the values are going to be 1, then it is going to act as an input port. When all the values are going to be 0, then it is going to act as an output port. Okay. So port 1 does not have any dual functions like your port 0, port 2 or port 3. So this is very specific to your input and output. Yes. So your 9th pin is reset pin. So your 9th pin is basically a reset pin. So this pin is used to reset the microcontroller to its initial values. Okay, so this is referred to as power on reset. So so this controller will be reset to your initial values. Okay, so resetting to the initial value in the sense you are resetting your program counter, you are resetting your accumulator. Accumulator is where you store the results. So you will load 0 to your accumulator, your program counter will reset to 0, your register B will reset to value 0, your program status word will be cleared, so it will be 0 will be returned to all, your data pointer will point to 0th location, and your stack pointer will point to 7th location. Okay, these are the basic resetting or the initial values of the microcontroller. So when you enable this pin 9, what happens? Your microcontroller gets reset. Resetting your program counter, accumulator, B register, program status word, data pointer, stack pointer. Yes, all the 5 elements will be reset to its initial value. So when you see pin number 10 to 17, so pin number 10 to apart from input and output operation, port 3, all the ports, port 1, port 2, port 0, port 3, everything is for input output operation basically. But they have got some additional functionalities as well. So now if you see, port 3 will also act as an input output port, but apart from it, you have the additional functions. So let's see, for each pin has got individual functions. So let's see what are the functions. So 10 to 17 are dedicated for port 3, and if you see the additional function, basic function is input output function. So additional, say your first pin of port 3 is for serial input port, serial data input. So it is receiving, so it is an input port. Okay, so now transmit data. So it is serial output port. Okay, so RxD, TXD. So your port number, your pin number 2 is external interrupt 0. You have external interrupts. So your your port 3 third pin is going to be external interrupt 1, INT 1, interrupt 1. 3.4 is going to act as timer 0, external input. External timer. So this is an external timer. So now port 3.5 is an external timer 1 input. So this is external memory write pulse. Okay, external data memory write pulse. External memory read pulse. Okay. So this is the alternate or additional functionalities that the port 3 pins are having. So from 18 to 19, you have pins that are interfacing your external crystal to get the system clock pulses. So this is your clock pulses for crystal oscillator pins, and your 20th pin is going to be the ground pin. Okay, so it provides the power supply combination. Yes. Next is pin number 21 to 28. So pin number 21 to 28 is the port 2 pins. So port 2 pins are usually again are used for purpose of input and outputs. But then they have certain alternate use also. When you see, port 2 is to supply higher order bits of address. It is used to send the higher order in the sense A8. So I told you address is in bits length. So address number A8 to A15. So higher is termed as higher order. So this pins are used to serve as higher order address bus along with the functionality of input output pin. So if you see, this is basic function is input and output operation. Apart from it, it has got also purpose of transferring the address, that is your higher order address. Okay, A8 only, A8 to A15 are the higher order address bus. Okay, higher order values, address values. So that is the purpose of port 2. Next is pin number 29. So this is this piece, and okay, this is going to be is the pin which is standing for program store enable. So this pin is an output pin. As you see, program store, it is used to read the signal from the external program memory. Okay, so it is based on the external ROM holding, which holds the program code. This pin is connected through the OE. So we'll see, understand what is OE pin of the ROM. So if you look into the ROM architecture, then you have something called as OE. So it is going to be enabled. Then you will have the access, or it can output the values through the external ROM. Okay, so that is the purpose. Next is that pin number 30. So your EA pin. So EA is nothing but external access input. So it is used to enable or disable the external memory interfacing. Next is your pin number 31, which is ALE. Okay, it is address latch enable pin. So it is used to multiplex whether it is data or address. Okay, so if you are so say, look into this point. So this is the ALE pin. So if it is high or low, it is going to determine whether it is address or the data that is being transmitted over here. So address latch enable is that your when it is high, your address lower order address bits are being transferred. So if it is low, then it is going to transfer the data value, 8-bit data, or if it is high, it is going to transmit the lower order 8 bits of your address. So higher order bits of the address are taken care with the port 2, but the lower order is being demultiplexed, going in a demultiplex operation with your address and the data. Okay, so it is this pin, ALE pin, which is going to determine whether the data transferred through this port 0 is address or data. Well, so next is pin 32 to 39. So these pins are known to be port 0 pins. And as you have seen, we have seen just now, it has the basic purpose of serving as an IO port, but it has also has the additional functionality to pass the lower order address and the data bus that are multiplexed using this port. Okay, the last pin 40 is going to be the power supply circuit, the VCC. Okay, it is related to the power supply. So this is the basic pin diagram of the 8051 microcontroller, and related functionalities we have seen. So next class we'll see look into the architecture of microcontroller. So with this we shall wind the class for today. Any doubts?